yesterday we stopped here. We went through this example quickly at the end of the class, but again, I will spend a little bit more time on it today. So, typically, like the examples we did in the MOSFET, you were given a device in a circuit. You have some missing parameters that you want to design, right? So, and you want to design it such that you put the transistor, in this case the BJT, in active mode. In this case, it's active mode. In the MOSFET, it was saturation mode. So, which means I would like to forward bias my emitter base junction, and I would like to make sure that my collector base junction is reverse biased. This is in the case of BJT. This is the summary. This is what you need to do: forward bias this, reverse bias that. Okay. So here you have 15 volts here, minus 15 volts here. How do we go about this? So before we go about this, just one thing to note: the way this is connected. See, the base is connected to ground. There's some terminology here in this chapter that is a little different than before. So this connect configuration now is called common base configuration, meaning the base is connected to ground and the emitter and collector are connected to the rest of the circuit. Okay, so because there's a common base configuration, there's a common emitter configuration, and then there's a common collector configuration. Depending on which terminal is connected to ground, that's what it's called. Yeah. Okay. Why these are advantageous, etc., etc. You will see that in the equivalent circuit models, we came up with an equivalent circuit model for the common base, and we came up with an equivalent circuit model for the common emitter. So sometimes when you see the circuit connected in a certain way, you may you resort to using a certain equivalent circuit just because of the way that the device is connected. Yeah. Okay, so this would be more clear in advanced studies of small signal analysis related to this, but so I don't think we will get there. But it's something you have to know the terminology. Okay. Okay. So let's go about this. So they give us, this is 15 volts, they give us beta is 100. And yesterday we talked about, beta is a device characteristic, right? However, this beta changes when you get into saturation mode. So it's a constant, quote unquote constant, because we said it varies a lot, right? So it's quote unquote constant in active mode, but it changes continuously in saturation mode. But by definition, beta is still IC over IB, the collector current over the base current. But when we are into saturation, we called it beta forced yesterday, right? So we called it beta forced when you get into saturation, right? And the measure for saturation becomes, okay, beta forced. What happens in saturation? In saturation, the collector current goes down and the base current goes up. So beta forced is less than beta. That I just wanted to refresh your minds about this. This is from yesterday's material. It has nothing to do with this example, really. Okay. So now, that being said, how do you go about? So now we are given beta 100. Again, VBE, the base to emitter voltage here, is 0.7. So if this voltage between these two nodes is 0.7 volts, right, with the base at a higher voltage, right? This is VBE, and it's a positive number, means the base is at a higher voltage than the emitter. How much higher voltage? 0.7 volts higher. So here my base is at ground, right? The base is connected to my ground, which means that the voltage here at this node, VE, is minus 0.7, right? This is equal to minus 0.7 volts. Okay, and at IC equals 1 milliamps. Okay, so minus 0.7 sorry, I shouldn't have put it here because it's minus 0.7 at IC equals 1 milliamp, right? But we're going to find out that IC is not going to be 1 milliamp, so let's see why. Design the circuit so that a current of 2 milliamps flows in the collector. So they're giving us IC equals 2 milliamps. So this will not be 0.7, but we know it's going to be we know it's going to be close to 0.7. I will put this in a square here. We know it's going to be close to 0.7, but it's not equal to 0.7, right? So we will have to calculate what it is. And like we did yesterday as well, now we have two conditions for current, where flowing through the emitter-base junction, right? One condition is where IC is 2 milliamps. We know that there is a relationship between IC and IE. IC is equal to alpha IE. And alpha depends on beta, right? So alpha and beta are related by what? Beta is equal to alpha over 1 minus alpha, or alpha is equal to beta over beta plus 1. Right? This is summarized in table 6.2 on page 367 of this textbook. So we know these relationships between alpha and beta. So which means I can calculate alpha. We know that alpha, when beta is 100, alpha is 0.99. Right? So which means that the collector, emitter current now is what? The collector current is 2 milliamps, which means that the emitter current is 2 milliamps divided by alpha 0.99, so it's a little bit more than 2 milliamps, and they calculated it as 2.02 milliamps, right? But this means that the voltage here is not minus 0.7, because this is minus 0.7 when the IC is 1 milliamp. Now IC is 2 milliamps. That means I have to resort to my diode characteristics, because this is current through a junction. This junction is like a diode. So I have to resort to my characteristics like we did yesterday, where we have, instead of the diode current, I can use this the current through the emitter, right? I can use the current. We can use the current through the emitter or the collector. Let's say we can use the current through the collector. Why can we use either this or that? Because at the end we're going to find the ratio, right? We're going to utilize this characteristic to find. And this is the voltage across the diode. What voltage across which diode? It's the base emitter voltage which we're trying to calculate, right? So this is VBE. Here we have two operating points. One operating point is 0.7 volts and 1 milliamp. 0.7 volts and 1 milliamp. Real is 0.7 volts, right? And we have another operating point, 2 milliamps, right? 2 milliamps flowing here results in another voltage. This voltage is what we want to put here. Do we see that? Okay. So then we do this ratio, right? Remember, we have I at operating point 1 is equal to saturation current e to the VBE over VT. And we get I1, I2, do the ratio, take the natural log, right? And then we will find the VBE, so we have current 1, we have current 2, we have voltage 1, so we're going to find this voltage 2, VBE. So in this case, VBE was calculated to be 0.717 volts. Instead of 0.7, it's 0.717, right? So instead of 0.7, it's 0.717 volts, right? So now this voltage here is at 0.717 volts less than the base, because now we are sure this is forward biased, right? Again, they give us the 2 milliamps, so we know that. We know that the base current is equal to the collector current divided by beta. So we know that. We know the base current here, and we know this voltage. So if we know the base current and we know the collector current, we can find the emitter current, or you can find the emitter current directly from here, from the relationship between the collector current and emitter current, which is alpha, right? So we can find that way. So now we know the current here, the current here, the voltage here, the voltage here, the voltage here, and then the condition was 2 milliamps in the collector current flows to the collector, and the voltage 5 volts appears at the collector. So this voltage they gave us to be 5 volts. So now finish, everything is defined. So I have the voltages across the resistor here and the current through it. The voltages across the resistor and the current through it. So I can find the resistor values in both cases. And now you need to confirm. So we confirm that this is now forward biased. is this junction reverse biased? Remember, this is a PNP transistor. So, sorry, this is an NPN transistor. This is NPN, right? So, this voltage was 0.7 volts. The base was 0.7 volts higher than the emitter, which means I have forward biased this, which is fine. That's one of my conditions for active region. What's the other condition for active region? That I've reverse biased the other junction. Reverse biasing this junction, this this PN junction means I have higher voltage on the N versus the P, right? So what do I have here? 5 volts. How do I have here? 0 volts, which means this junction is also reverse biased, right? So now we understand that this is an active mode. Any questions on this example? Okay, so they go through it, blah, blah, blah. Like we did for the MOSFET, we can look at the temperature dependent. So we know that the current, the collector current is related to the base emitter voltage using the exponential, right? So we can draw the exponential characteristics IC versus VBE, right? If we look at the relationship, it depends on temperature, right? So it's IS e to the VBE over VT, and VT is temperature dependent, which means if I change the temperature, the relationship between IC and VBE will change. So they just talk about that. So they show the plot at different temperatures, which is something with so like the diode, it can be used like a temperature sensor. So there are actually MOSFET temperature sensors, and so there are MOSFET and BJT more MOSFET temperature sensors than BJT temperature sensors. Yeah. But you can use it that way. And one thing that is to note is, again, when the temperature increases, the voltage decreases across the device, right? It's called the negative temperature coefficient device. This makes it a bit more challenging to put devices in parallel. Because what you want, when you put devices in parallel, you want to make sure that they share enough current. They share the current, right? So what happens when a device has more current than the other? It should get hot. If it gets hot, what do you want it to do? Theoretically, you want it to resist more current, right? But here, when it gets hot, for the same value of, for example, for the same value of voltage, let's say for the same value of voltage, which means for the same value of voltage across the device. So let's say I have a curve close to here. The same value of voltage, when it gets hot, actually it's gonna draw more current. Do you see this? So negative temperature coefficient devices are very difficult to parallel. A MOSFET actually is a positive temperature coefficient device. So this is something, I mean, this is more advanced, but something that to consider when you look, I mean, this is a reason why they talk about this stuff. So that, you know, if you talk about paralleling devices, for example, later, okay, which devices do you want to parallel? Devices with negative temperature coefficient or positive temperature coefficient? Definitely positive temperature coefficient, because if it gets hot, you want it to resist increases in current. And then what will that do? That if you're going to resist increases in current, that means the current will flow through the one that's a bit cold, warmer, colder, right? Less hot. Meaning that one will now get hot. Its temperature will rise. It will resist. So then, at the end of the day, the device currents will balance each other out, because they all want to operate at the same temperature. These devices, not the case. This one, oh, it gets hot. Oh, allow more current to go through. Allow more current means more power loss. More power loss means getting hotter. So it's like a positive feedback. It's going to burn itself, right? So that's why MOSFETs actually are quite a bit utilized at higher temperature applications. Yeah. So this has applications. This has applications.
It's a positive feedback is bad.
Yeah, but I mean, in this application, when I'm trying to parallel devices, right? But maybe it has other applications,
Okay.
right? And it's only in, I'm giving you a special case where this is not, where the MOSFET may be nicer to use in a certain application, right? Okay. Like we did with the MOSFET as well. Okay, so when we came up with the model, or the equivalent circuit model for the BJT, we said it looks like what? Huh? We said that the IC versus VCE characteristics look like this, right? Straight. This was IC versus VCE characteristics. Correct? Yes? No? This was yesterday, I think. Okay, so like the MOSFET, the benefit of that was very clear when we drew the several characteristics, and we said that these are characteristics of IC versus VCE at various values of VBE. Where is this coming from? Remember our model, our output model looks like what? I have a current source. The equivalent circuit model looks like what? It's a current source that is controlled by what? IC here is controlled by what? IS e to the VBE over VT, right? This is my current source. This is my emitter. This is my collector. This is my emitter, and this was my base, right? This was the base emitter junction. This was VBE, and this was the equivalent circuit model, the common emitter equivalent circuit model for the device, right? What does this equivalent circuit model mean? It means that if I change VBE here, the voltage across my input due to current, basically, so I've pushed enough current, I've forward biased this diode, I've created 0.7 volts across this diode. So changes in VBE will cause a current in the output that is independent of VCE. That's what our equivalent circuit model told us, right? So, which means that I can plot IC versus VCE, where this equivalent circuit model that we came up with was only in the active region, right? So only in the active region can I model the device this way, which means that in the active region, which is here, right? This is my active region, this zone here, right? This is the active region. The active region, if I change VBE, 1, 2, 3, it will change the value of IC. IC here, IC here, IC here, right? But changes in VCE do not affect the values of IC, right? That's what this equivalent circuit model showed us, yeah. Right? So this was the ideal equivalent circuit model, not including a certain effect that we also talked about in the MOSFET. What happened when I increased in the MOSFET? I increased VDS considerably. When I increased VDS considerably, we saw that it had an effect on the drain current. It increased it slightly due to something called early voltage, right? Here, it's exactly the same. Remember, increasing this slightly will increase the reverse bias of the collector-base junction. What is the reverse bias of the collector-base junction doing in the BJT? Remember, this is my device. This is my emitter, base, collector. Reverse bias, and this is my N, P, N. Reverse biasing this did what for us? It put an electric field this way that the diffusing electrons that diffuse from the emitter to the base, when they moved in here into the base, they saw this, they were met with this electric field that pushed them over outside the collector, right? So it collected them in the collector, right? So if I increase VCE, I'm increasing this electric field, hence I'm increasing the probability of these electrons flying through. So it will find more electrons to push through across the barrier, right? So is it a significant effect? No, of course here it's amplified, right? So it's ideally, we'll consider it a straight line. But if it's gonna find more charges to move over, which means it will increase the current with VCE, right? So before it was not. Before VCE changes were not affecting my model at all. If I want to consider early voltage, then it's like, when we've pinched, in MOSFET, after you've pinched and the effective channel length modulation, what the effect was? What was the effect? The effect was increasing current, meaning the slope here versus a straight line. Same thing here. Increases in VCE will do the same thing. I will increase current a little bit. Again, this is magnified just for convenience. Yeah. And then the same exact phenomena, the slopes of these lines intersect at a voltage VA called the early voltage. Exactly the same as the MOSFET, discovered by the exact same person. Okay, so the effect is what? The effect is an increase in current. So I will now rewrite my collector current equation, but instead of it's IS e to the VBE over VT, it will increase by something that depends on the early voltage and depends on VCE, right? So that's what they're talking about in discussing in this section. And the slope of this line, okay, the one thing. So this is this additional increase in current that we're discussing. The slope of this line, this is what? This line is changes in current versus voltage. So delta Y is current and delta X is a voltage, right? If this slope here, the slope of this line, delta Y over delta X, is the current over a voltage, which means it's 1 over a resistance, right? So, which means that I can sort of model that in my equivalent circuit. I shouldn't have erased my equivalent circuit.
Do we have to increase the voltage?
Sometimes you do. Sometimes you want to increase the voltage.
All VGT.
In what? Well, it depends, because remember, we will solve an example where we will increase VCE and see what happens. Yeah, and at some point, increasing VCE will not help increase IC. Because of what? Because we are in saturation, for example. If you're in saturation, increasing VCE has no effect. But if you're in active mode, it will have some effect, right? So, because you remember, VCE is what? VCE, if we looked at our device, right? VCE was the voltage between my emitter to collector. This was my base. This was VCE. It's equal to VBE plus VCB, right? If I increase VCE, meaning I go this way, for a given VBE, meaning I'm on one of these curves, right? Because one of these curves is a specific VBE, right? Am I increasing VCE for a given VBE? It means that VCB is increasing, right? Which means that the collector-based junction is seeing more reverse bias, meaning the higher electric field I was talking about, right? So, do you want to do that or not? We will see applications where we want to do that. We will increase VCE at some, because again, the operating point of the device depends on the values of the resistors that I have here, right? At some point, the example we saw at the beginning of the class, based on these values of the resistors, I'm fixing the voltage here at a certain value, fixing the voltage here at a certain value, meaning I'm putting the device at a certain operating point. We will see that, like the MOSFET, we will have a voltage transfer characteristic. So far, we had what? We had a voltage input, and we had a current source output, right, at the emitter. So we had the current source output between the collector and the emitter, right? This was my current source output IC between the collector and the emitter, and this was my base emitter, right? So here, the value of the current is not changing at all, right? Value of IC is not changing regardless of VBE, right? If now it's changing, it means that I can model that as a resistor, like we did with the MOSFET. Some are up. If I put a resistor here, this current flowing through the collector will have to be divided between this and that, right? Which means it's going to affect the value of affect this slope, right? So this slope I will represent as this resistor. Okay, and we will see. I'll go through an example where we're increasing VCE, and at some point we'll see that it's not going to be very helpful here. Okay. So they talk about the slope here and creating the value of our output. What is this equal to that we can show from, they solve for our output here. For example, they differentiated this with respect to VCE, and they called it our output and solved for it. And then the result was this. If you want to do this as a bonus, feel free to do this as a bonus. Differentiate this ICE with respect to VCE at a constant value of VBE and show that our output is equal to this. It is for sure, but they didn't derive it yet. So this can be a bonus, yeah. So, and then so then they do what? Then they and this is the actual value of IC, considering what? This is IC considering the early voltage. And then they if you substitute with IC not considering the early voltage, right? So IC considering the early voltage is this equation. So with this addition, IC, the collector current without the early voltage considered is, you remove this, right? So you can rewrite the equation for our output in terms of the collector current with and without considering the early voltage, right? So just another form of the equation, okay?
Without the early voltage?
No, it's IC without the early voltage, VC, this term goes away, right? This term here goes away. This term goes, only the second term here goes away, right? If I don't consider the early voltage. So they just called this IC prime, right? They called it IC prime and they wrote it here. So our output, and this IC is actually IC with the early voltage term considered, right? So that's why the equations for our output changes from here to here, and again it can be part of that bonus.
We have VA.
Yeah, given VA, but do you have?
So VA is not from the.
No. VA is the intersection of these slopes with the horizontal axis, and that's typically a number you will, it's a device characteristic, right? It's a characteristic depending on the actual device.
So it's not VA.
So it'll be given.
So it's not VA from IC.
VA from IC.
Yeah, from the equation.
No, VA is an early voltage. It's a characteristic of the device. Yeah, IC and VCE are what? IC and VCE are operating points, the DC operating points of the device, right? Which DC operating points? This is the DC operating point for current, considering the slope. This is the DC operating point for the current, not considering the slope. That's it, and that's so if you just, it's a reordering of the equation basically. Okay, if you do the derivation, I didn't do the derivation honestly. If you do the derivation and find the equation for our output, you will be able to see that fine. I can remove some terms from the equation and rewrite it in terms of IC prime, which is the current without the effect of the slope basically. So you can use either of those equations to calculate our output. That's the conclusion here. But again, like we did for the channel length modulation and many of the problems, from a design perspective, we will initially, maybe ignore that. And because typically you do what? Typically you design a circuit. Typically you will design a circuit and then you will do what? Then you will simulate it. And typically in simulation, you will actually simulate maybe two levels. You will simulate with an ideal device. And then maybe simulate with the actual device, including the early voltage effect and the slope on the current. And then you look at, okay, what's happening in your circuit? Is it considerable or not? If it's not considerable, it doesn't affect your application, right? It will be application dependent. If it doesn't affect your application, then it's fine. Then you move on, right? So that's why a lot of the stuff we're doing is, okay, approximately. You will see a lot of the stuff they say, okay, approximately equal to, right? Because initially you want to design the circuit here. Again, this is the complemented circuit with our output in terms of the base emitter voltage or in terms of the base current. Remember yesterday we showed equivalent circuits where we had a current source that is voltage controlled and the current source that is current controlled. And this is IC. This is basically IC, and then we know that IC and IB are related by beta. So I can just replace IC with beta IB, and have it a current, which means what? Which means I can draw a characteristic now of the device instead of drawing it at constant values, different values of IB, right? And that's what they do next actually. So here we were drawing IC versus VCE at different values of VBE. 1, 2, etc., right? That's what we just saw. I can do the same, but at different values of IB. Correct? I mean, this is what this means. This is what this means. It means that IC will be controlled by VBE, regardless of VCE, right? Regardless of VCE. But regardless of VCE is not true because now I have a resistor here, right? If I don't have the resistor, it's regardless of VCE. And here what this means is IC is controlled by IB, regardless of VCE. But when I put this resistor, it's not the case anymore. This resistor will affect, and it will add these slopes that I have, that we talked about. Okay? So these are some equivalent circuit models, including the early voltage effect.
Adding the resistor will make the circuit not ideal.
Adding the resistor will make it not ideal, yes, sure. Will make it closer to realities by including the early voltage effect. Okay, so now in the next section they talk about what I was just talking about. Instead of drawing the characteristics with respect to IC versus VCE, with respect to different values of VBE, it's with respect to different values of IB, right? It's equivalent, right? It's the other equivalent circuit model that we showed here. Then they sort of zoom in, closer on the saturation region. So again, I did this before, and I just want to reiterate, right? So beta here, beta and this, beta is a characteristic of the device. So beta will be IC over IB, which will also be called if you look at our device here, it will be called the common emitter current gain. Why is it called the common emitter current gain? Because this is my common emitter equivalent circuit, and I see beta here. So it's not, you don't have to memorize it's a common equivalent. If you just see the equivalent circuit, you should know that beta is called the common emitter current gain, and then alpha was the common collector current gain. Common base current gain. Because if you go back to the common base equivalent circuit, you will find alpha is affecting the current gain in the common base. Beta by itself is called the common emitter current gain. Yeah. And we talked about in the beginning of the class, I reiterated the importance of beta versus beta forced, right? I reiterated the idea of beta versus beta forced at the beginning of the class. Why is this important? Because in saturation here, we're zooming in on saturation. In saturation, what's happening? In saturation, fine. IC is still beta IB. IC will always still be beta IB, but the beta will change. It will not be a device characteristic like the device characteristics used in the active region anymore. It's not going to be 100 anymore. Yes, because in the saturation, the gain is changing. The slope is changing. In the active region, the slope was not changing. So beta was constant. Every time you increase beta, IC will increase. Every time you increase beta, IC will increase, right? You increase beta, IC will increase. But now, here, what's happening? If you increase the IB, IC will increase, but is it the same increase that we had before? No. So we said that this beta is called beta forced, and it's less than beta of the device in active mode. So they're just reiterating that. The other thing they're talking about in this, they're introducing this section is, okay, the slope of this line here in saturation mode is what? Is also a change in current over a change in voltage, right? Which means it's also 1 over a resistance, equivalent to 1 over a resistance. And this resistance, this slope is pretty high, which means the resistance is pretty small, right? So if the slope is high in this case, the resistance is very small, which is nice for switch applications, right? And that's why we operate, if we're going to operate a device as a switch, on-off, just an on-off switch.
open circuit or short circuit. But when it's short circuit, there's a drop. What is this drop equal to? It's an equivalent resistance multiplied by the current flowing through it, right? This resistance now is very small because of the slope here being very high. Right here we zoomed in considerably on the saturation region here. So, and that's why the device, when you want to operate as a switch, you either want to operate in cutoff, open circuit, or you want to close the switch and operate with a small voltage drop. Do you want this R to be big? Do you want this RCE saturation? They call RCE sat. Do you want this RCE sat to be big? You want the switch. A switch is ideally either open circuit or a short circuit with no drop across it. So that's why this is physically what we get when we start pushing the device into saturation mode, meaning forward biasing the collector base junction. Remember, the collector base junction was reverse biased. We start forward biasing the collector base junction by decreasing VCE. How is that affecting the collector base junction voltage? Again, draw your device. Emitter, base, collector. This is VBE. This is constant for one of these curves, right? This is VCE. This is VCB. If VCE is going to go down, and at a fixed value of VBE, what does that mean? It means that this VCB is decreasing, right? Right, for a fixed value of VBE, right, on one of these curves. One of these curves means a fixed value of VBE. If I'm on one of these curves, meaning this is fixed, and VBE plus VCB is VCE, right? If this is fixed, then how can this decrease? This is decreasing now. By decreasing VCB. Until when? Remember, this is about 0.7 volts. It means that if it's going to go beyond, if this is 0, then VBE is 0.7, and I'm still up here. Right? VCE, sorry, if VCB is 0, VCE is equal to VBE. And we're up here on this point, at this operating point. I'm not here. I'm pushing this device into saturation, which means I'm making VCB negative. Because remember, I have to make it negative to forward bias the collector base junction. Negative by how much? We said that fine, about 0.4. 0.4, if this is 0.7 and this is minus 0.4, then the difference is, about 0.3. So this is the edge of saturation here, around 0.3 volts, the edge of saturation. If I push it even further, minus 0.5 or minus 0.6, then I'm deep in saturation, right? Which means VCE, deep in saturation, is about 0.2 volts. Right, about 0.2 volts. This is deep. Here I'm deep in saturation. Right, this is edge of saturation between active and saturation. Here I'm deep in saturation. So when I'm deep in saturation, the voltage drop here is about 0.2 volts. Triode region, that's the confusion. So in the MOSFET, we call this triode region, and we call this saturation region. Cutoff is cutoff. It's easy. Cutoff, no current is flowing. This is the zero axis, all right? But they mixed this. This is a bit mixed up here. But we see the value of it, right? The value is the VCE becomes very small. Means the voltage drop, equivalent voltage drop across the junction is small, which is nice for what? For very high voltage applications, right? For if I'm using a BJT in a very high voltage application, meaning a VCE that's very high. The answer to your question, right? If VCE is very high, meaning a power application, right? Why is that very interesting? It's interesting to put the device in saturation mode and triode mode because the voltage drop across the device is very small. So regardless of the current you're pushing through it, what's happening? I still am maintaining VCE about 0.2 volts. So it's a nice device characteristic. But is this nice for low voltage switch applications? No. If I'm operating with 1 volt, 0.2 of that I'm seeing across the device. That's not very interesting. In the MOSFET application, you will see that this in triode operation mode, the value of resistance is very small, even small, much smaller than the BJT. The slope is even higher. So in this case, operating with a MOSFET as a low voltage switch may be very interesting. Operating a BJT as a high voltage switch may be very interesting, right? So this has applications and this has applications. Yeah. Okay. So to model this device in deep in saturation, we can use this simple equivalent circuit mode, right? When we know we're in deep in saturation, we know that this is going to be the model of the device. We're okay with this, with the model of the device, being 0.2 here and 0.7 here. 0.2 is the difference between 0.7 and 0.5, right? It's this, and this is now the voltage across the VCE junction. So regardless of how much voltage I put between my collector and emitter, I see a VCE of 0.2 volts, which is nice. So when the device is in saturation mode, right? Meaning, no, in power, in very high voltage devices where you're trying to operate in saturation mode, you're not going to try to put resistors in series with the device. You will have your motor windings. You will have the filter inductance. You will have your power currents. You will not try to add more resistances there. In the active region of operation, that's where you want to put these resistors to try to fine tune, okay, where you're going to operate. And why is that important? That's what we're going to see next. Yeah. But okay, so here, this is a good example where it goes through, okay, you have a device, okay, put it in active mode, and then put it at edge of saturation, and then put it at deep saturation. And then, solve the circuit in different cases, yeah. So it also helps answer one of your questions about, increasing the value of the supply voltage, for example, and seeing what the effect was. Okay, so here they have the circuit. They want you to determine the value of the base voltage that results in the transistor operating in active region, edge of saturation, and deep in saturation. And in the active region, they're telling you beta is 50, and VBE remains constant at 0.7, because we saw that it's 0.7, 0.717, 0.69. It doesn't really matter. They just said assume it's 0.7. Yeah. So I know that this is at 0, meaning this voltage here is what? In active mode. Oh, this is 0. So what's the value of voltage here in active mode? .7. Here they give you. They said VBE is 0.7 in active mode, right? So this is 0.7 volts, right? So this is 0.7. They gave us in active mode. The VCE is 5. So this is 5 volts here. Which means I know the voltage here. I don't know the voltage here, but I know the resistance, right? What else? Do I know the current? Not yet. Let's see. So I will find the current. So I know this voltage. I know this voltage. So I know the voltages across this resistor. I know its value, so I can calculate current. If I can calculate current IC, I know that IB is equal to IC over beta. Beta is given as 50. I can calculate IB. IB, if you know IB and you know this value of resistance, you know this 0.7, you can calculate the value of VBB to operate in active mode. Okay. How about at the edge of saturation? What did we say happens at the edge of saturation? We will not have VCE equal to 5 volts, obviously. What is VCE equal to at the edge of saturation? The edge of saturation, deep in saturation, what is VCE equal to? VCE sat, we will assume it's 0.2 volts, right? At the edge of saturation, let's say VCE will be about 0.3. So we will assume this to be about 0.3 volts. And then we solve again and calculate VBB, same thing. And then deep in saturation, we solve again, put this as 0.2 volts, and solve again and see what happens to VBB, right? No, 0.7 is the base emitter voltage. Why is it 0.7? Because this is my P, this is my NPN junction device.
Yeah, because of the average.
Because what's your question again? No, this is 0.7 because this PN junction is forward biased. Remember when a diode is forward biased, it's if you designed it so that the concentrations are such that you have a barrier voltage of 0.7, you will get 0.7. That's typically what we designed the barrier base emitter voltage to be. Okay.
We have VCE as 0.7.
VCE is 0.7. No, that's not. That means that we're not above, not in saturation, right? Because the borderline is about VCE is about 0.3. Remember, VCE was the addition of these two. This is 0.7. This is my VBE, and this is VCE, and this is VCB. Right? This is 0.7. 0.7, and if you're saying this is 0.7, it means this is 0. This is 0, and this is 0.7 is my device in active mode or in saturation. Yeah, active mode. I mean, the device, the collector base junction will be forward biased when the collector base voltage is about negative 0.4 or more, negative 0.5, negative 0.6, negative 0.7, right? But if it's negative 0.3 or negative 0.2 or 0 or 1, then it's reverse biased. It's not forward biased. Yeah. So I would be in active mode if VCE is 0.7. Yeah. So they just put some comments here about, okay, so if you look at the value of so this was in the first case, in the active region, VBB was about 1.7, right? At the edge of saturation, VBB was about 2.64. Deep in saturation, VBB was 10 volts, right? Very different. I mean, do the numbers, right? But the idea is, here it's 10 volts. And look at the base current. Base current was, in the active region, 0.1 milliamp. And at the edge of saturation, base current was 0.19. Not too much of an increase. Deep in saturation, how about that? It's 0.9. So the base current increased considerably, right? But now let's look at collector current. Collector current was at active region 5 milliamps. At the edge of saturation, 9.7 milliamps. So what happened? What happened was I increased VB to 2.64 from 1.7, right? So the base voltage was increased, hence the base current was increased from 0.1 to 0.19, right? And because I have a nice beta, then I got a huge increase in collector current from 5 milliamp, right, to about 10 milliamps, right? So because of my beta. Now, in saturation, I have a beta forced, right? That is much less. What does that mean? That means even though I increased IB in my base current, and I've increased the base voltage, what happened to my collector current? It was 9.7, and now it goes to 9.8. Not much of an increase. So I've lost my gain in saturation mode, right? There's in saturation, that just describes what we were talking about, right? This beta forced phenomena that we discussed. So does everybody see this example? Okay. So again, like the MOSFET, what we've done in the previous examples, we didn't sort of formalize the idea of operating point. But basically, that's what we did for because we studied the MOSFET, we know that everything we did before was sort of putting the device at a DC operating point, right? But we didn't formalize it or introduce it as such, right? So now we will just formalize it and introduce it as such. We will formalize what we've done before as putting the device in a DC operating point, right? But that's exactly what we did. Put these resistors around it, and played with the values of voltages and currents like we saw in the last example, to put it in active mode, saturation mode, cut off. We can design the voltages, the values around it to make sure that we are putting the device where we want it to be, right? So now you're going to be given circuits, and then these circuits will have a DC operating point and a small signal, like we did for the MOSFET, exactly the same, except all the terminology is different. right? So, but the solution process is very similar, and and the logic is also very similar. So we will do the small signal analysis the same way. So we have now this device that will either be in cutoff or conducting. And when it's conducting, it's either going to be in saturation or active region, right? These are our possibilities that we have, right? So how do you go about solving? Like we did for diode circuits and like we did for the MOSFET circuits, we will have to assume a condition, right? Because you don't know if the device is active or cut off or saturation, right? So you will have to assume a condition. So for example, the process in this section here, that what they did was describe what the process should be. So you would assume, for example, that the device is active. So assume it's in active mode, and then you would check your voltages. Yeah, you solve your circuit. You assume it's in active mode, and you solve your circuits. Find the value of VC, VB, VE, and check. What do we check? We check that VCB, for example, my collector base voltage is greater than negative 0.4 volts, which means meaning minus 0.3 or minus 0.2, right? So the collector base junction is still reverse biased, right? So it's still reverse biased. So if it's still reverse biased, then fine, I'm in active region. How about if it's not reverse biased? If I'm putting a negative, if VCB is minus 0.5 or minus 0.6, what? Then it's either going to be in saturation or cutoff, right? So you have to assume you're in saturation. Assume you're in saturation. If you assume you're in saturation, then you will calculate. What did we said is a good check for saturation mode? Saturation mode, you calculate beta forced. And make sure that beta forced is less than beta that you were given. If that's the case, then you're in saturation mode. Okay? Yes.
For CCB, we get them minus 4.4.
Yeah.
Isn't it the edge?
Yeah, but I'm saying bigger, not equal to. Sure. I mean, bigger meaning it's not equal to it.
So
Like,
it's equal to it's
yeah, equal to it's the edge of saturation. Equal to it's 0.3. Again, it's not a fixed value, right? We agreed that we will say that it's about 0.4, right? But it's not sharp. But you just have to know that fine. It means that this collector-based junction is being pushed into forward bias, right? So this will be the solution sort of process or steps that they describe in this big section here, right? So they spent all this time describing this, and then they've sort of summarized our equivalent circuits that we've put for a PNP and NPN. So now we will solve a PNP example so that you are comfortable with that as well. So we only solved NPN examples so far. Well, I'll solve a PNP example to give you some reassurance. Yeah. Okay. So here, there's another NPN. So we'll do one more NPN example, and then we'll do a PNP example. So this is very similar to, again, the example that we just did. So I'm going to go through it very quickly. Right. So here, we consider the circuit shown, which is redrawn to remind the reader, blah, blah, blah. We wish to analyze the circuit to determine all node voltages and branch currents. Same, right? It's the problem is always the same. Yeah. We're either going to be missing the resistor values, or we're going to be, okay, you're given the resistor values, given the supply voltages, okay, is this device in active saturation, etc., etc. So this is equivalent, of course, to this, right? These two circuits are exactly equivalent. They just redraw it, and then they give you beta here assumed to be 100, right? So that's something they give you. So they gave you the resistor values, and they gave you the beta, and then they gave you the supply voltages, right? So how do you go about solving this circuit?
we can check the saturation by beta.
First, we will assume. No. What did we say? We will assume we are in active mode. No. 0.7 is one value for VCE in active. Active means the base emitter is forward biased. The base emitter junction is forward biased. That's active. So base emitter junction is forward biased means what? Means this is my base, this is my emitter. Means this is 0.7 volts. That's what this means. Okay? So, which means that the voltage here with respect to this The difference is 0.7. They have defined the voltage here to be 4, which means the voltage here is what? Exactly. Right? So if this is 4, this is 3.3, then this is, I have the voltage here on this side of the resistor, and this is 0. So I can calculate IE.
Which is equal to
From IE, I have IC is equal to alpha IE. And alpha can be calculated from beta, right? So now I can calculate IC, and I can calculate
You can find
IB, right?
by dividing by beta.
By dividing by beta, exactly, right? So now I have the current here, the current here, the current here, and I can calculate now. What's the only thing left? The only thing left now, because I want to see if this device is in, where is this device operating? So the only thing left is I need to calculate VCE, this voltage with respect to VC with respect to ground, or VCE, yeah, right? I can calculate, but typically we will, yeah, it doesn't, yeah, you can calculate this voltage with respect to ground. That's because we know the voltage here with respect to ground. If we can calculate the voltage here with respect to ground, then I will know the difference between these two, and I will know if this device is in, if this junction, if this NPN junction, if this NP junction is forward biased or reverse biased, right? So then this voltage is equal to what? VC is equal to what? 10 volts minus the voltage drop across this resistor, which is equal to the current that you've calculated, IC, multiplied by the resistor value, right? So that's basically it, right? So the value for that is 5.3 volts. VC, if we do the calculation, it's 5.3 volts. If this is 5.3 volts and this is 4, is this collector-based junction, CBJ, forward biased or reverse biased? Reverse biased. On the N side, I have a higher voltage than the P side, right? So they can even be 0. It's okay, and they can even be negative. This voltage VC with respect to VB can be negative, but if it can be negative 0.1, 0.2, 0.3. But if it's 0.4, then okay, then I'm starting to push this into forward bias. But now it's highly positive, right? Then I'm reverse biasing this for sure, and this is an active region, right? Okay, so that's this example. You can go through it. There's one example on a PNP, not an NPN. Example 6.7. It's exactly the same, but just so that you are familiar. I mean, in your homework you will have a PNP example, but this is just. You will see that it's exactly the same. The equations are exactly the same, and the condition. As long as you understand the condition, I want to forward bias my base emitter junction, and I want to reverse bias my collector base junction. So we. Different drawing, yes, different drawing, I agree. The symbol is different, and we discussed the symbol yesterday. And we said that this is always the emitter. Where the arrow is always the emitter. So this is the emitter. Yeah, always the emitter.
I thought it was the emitter was going down.
No. Emitter is the arrow.
The arrow is the emitter.
Arrow is the emitter. Arrow is the emitter. We said this yesterday.
So find the emitter, we know the base.
So this is my base emitter, and this is a PNP. PNP. Right? So I want to make sure that my base, my PN, this junction is what? This is PN. I want to make sure this is forward biased. Right? So forward bias being the voltage here becomes 0.7. That's, analyze the circuit, determine the voltage at all nodes and the current at all branches. Let's see. So first, again, we said we will assume. First step is assume that we're in active region. So assume active region means I assume this junction is 0.7 volts. This is at ground, which means that the voltage here is 0.7, just because this was at ground. So now I have this voltage. I have this voltage. I have this voltage across this resistor. Then I can calculate the current. Right? I can calculate the current. What current is this?
IB. No, IE.
Exactly. It's emitter current.
So then they
Right.
got alpha.
So emitter current, which means I can calculate
I see.
collector current. Remember, collector current is alpha IE. Alpha is when beta is 100, alpha is 0.99. Right? So I can calculate IC. IC, I can calculate IB. Note the IB isn't coming out of the device.
Oh,
Right? Like if you look at the equivalent, yes, always coming out of the device. All the polarities of all the currents have changed.
Alpha.
Right? Because remember, initially in the NPN,
it was entering.
the current was entering the collector.
And it was there in the emitter.
Exactly. Now I flipped, because I flipped the device.
The emitter is entering.
Exactly. Here the emitter entering current, the collector exiting current. But base current is also flipped. This is but the process is exactly the same. Okay, so yeah, it's
Alpha
easy.
is given.
As soon as you have beta, then you have alpha, because beta is equal to alpha over 1 plus alpha, and then alpha is equal to beta over 1 plus beta, something like that.
Why would I get beta?
They gave it to you. They gave it to you. I think we want to analyze circuits. I think they will tell you if you're not given. Assume here. They tell you that it's they tell you that since no value for beta has been given, we shall assume 100, right? But you will be given that. It's so if that's the case, then that's it. It's a easy circuit to solve. Everybody's okay with this? Comfortable with this? Okay. So now, now class is over. Sure, but I want to show you something interesting, and then we'll. So they have a more complicated circuit here, for example. They have two of these BJTs, one NPN, one PNP. I just want to show you one thing. When you put these one application of something like that, this is called the cascode amplifier. All right, cascode meaning if I have these two devices, after each other, and what's happening here is the beta will increase considerably. So if you look at beta is what? The ratio of the IC to IB, and the ratio of IC to IB, or IC to IB, right? You will see that you got some gain. This was IC 1.25 divided by 0.013, right? And then when you put another device in cascode mode or in cascode configuration, you got more gain. So your sensor was here, right? Your sensor was outside this amplifier, right? And then this is your new output, right? So I've been able to construct a device with much more gain. You see now why op-amps are made of many of these devices? If you want to create something with a very large gain, so you do not use, once you have many of these devices inside the op-amp, right? So that's one thing I wanted to show. And then I'm not going to solve it. You can solve it. It's
For tomorrow's exam, are we gonna have like complicated circuits like this?
complicated circuits. No, I will not give complicated circuits. I'm just being honest with you here. But I expect you to know the theory. Okay, so I will have a theoretical question. So just out of yeah. See, now Ahmed doesn't like that. Yeah. But so next on BJTs, the next thing we'll do is, the voltage transfer characteristic, and then small signal analysis. Exactly. When it's exact, it looks exactly the same as what we did for the MOSFET. Exactly, really, the process is exactly the same, just some terminology changed here. Okay, so we'll stop here today, and we'll continue tomorrow. As you see, we're wrapping up in the same. We're wrapping up the section 6.5 of the textbook. We will stop. I will look at 6.6 just quickly, but I will not cover it in detail. Like same place as we stopped for the MOSFET.